Okay, so I am now recording. Please, if you are you do not agree with recording, just tell me, or you don't have to switch on your camera. Yeah, so I'm recording now. There is the reason I wanted to review this whole effect is to mention some, because we will do a review session, and I wanted to have some remarks about it, about the whole effect. Now, let me just give the case where we have this thing. Okay. So we have this, and let's assume I am applying the electric field here, and obviously, if the so this is the, I will take it as the axis, x-axis, and the y-axis. Now, if I apply, of course, the drift velocity is going this way, right? The drift velocity is going this way. And if I apply, let's say I apply the magnetic field along the x-axis. If I apply the magnetic field along the x-axis and the drift velocity along the y-axis, what will be the magnetic force? The magnetic force will be the charge of the electron, the drift velocity across the magnetic field. Who can tell me in which direction the electrons will go? Now, first, before doing this, I will, so the phase that is, this is phase number 1. This is phase number 2. The other phase in opposite to phase number 1 is phase number 3. The top phase is phase number 4, and the bottom phase is phase number 5, and the phase that is opposite to phase number 2 is phase number 6. So this is an object that has 6 phases, 6 phases. So now, in which direction will the magnetic force be directed? Now, let me also explain. Phase number, for example, phase number 1 and 3, they are perpendicular to the y-axis. Phase number 2 and 6, they are perpendicular to the z-axis. And phase number 5 and 4, they are perpendicular to the x-axis. Now, in which direction the magnetic force, this magnetic force, will be directed? Yes, okay, to Z. Are you sure? In which direction the force, magnetic force, will be going?
I'm a fucking electrical engineer. Why tiny force?
So I'm talking about the magnetic force. Okay, the magnetic force. So let me explain here. This is the drift velocity, right? And this is the magnetic field. So this is the z-axis. This is the x-axis, right? So when I do the cross product, VD cross B, I'm going in the page or out of the page? Hello? Okay, so I'm going out of the page. Very good. Now, do you all agree? The cross product, I'm not talking about the force. The cross product, V cross B. I'm
Yes.
going out of the page. Now, because of the negative charge of the electrons, so the force will be going inside the page. Right? Do you agree? So now, if the electrons now are pushed inside the page, in which phase they will accumulate? In which phase they will accumulate? Will they accumulate in phase 1, 2, 3, 4, 5, 6? In which phase they will accumulate? So now I have the electrons going into the y-axis, negative axis, y negative axis. This means they will accumulate in which phase? Which phase will become negative? Yes, I have a good answer. Yeah. Yeah, Rhoda, good. Okay, any other answer? Yeah, so the one in the back, the one in the back is which number? You are right. So it's number 3. So number three, yes, you are right. Haya, Jasim, you are right. So number 3, this phase becomes negative, and phase number 1 becomes positive. This means that there will be an electric field, a whole electric field, that will be created between this phase and this phase. So this means if I look at a voltmeter, if I use the voltmeter, I will be measuring a potential difference that is called the whole potential difference. And this will be the electric field divided by the distance, which is the distance between phase 3 and phase 1. Is this clear? Okay. Okay. So I just wanted to mention this because I might give you other situations where the electrons will accumulate on phase 4 and phase 5. So then you have to choose this distance. If I asking you, okay, calculate the potential difference between the two phases of the whole effect. Okay, so please pay attention to the way you define first the direction of the magnetic force, the direction of the whole electric field, and the difference and the potential difference, which will be used to calculate the which phase will be used to calculate the whole electric field and the whole potential. Okay. So that's what I wanted to mention. Any question about here? Yes, the distance between, exactly, the D is the distance between phase 1 and phase 3. For example, if I'm telling you this is just to make it clear, you know, in this situation, okay? Let's assume that I'm telling you, okay, this distance is, let's say, 2 millimeters. This distance is 6 millimeters, and this distance is 10 millimeters. In this specific example, the 6 millimeter is the one that should be used just because the electric field is created between this phase and this phase. So the electric field is in this direction, so along the phase or the distance of 6 millimeters. Yeah. Okay. But I just wanted to mention this so that you don't get confused. we will do some problems about it, but let's give this example before going to the next. Let's give this example. Okay. So, can you please mute because it just disturbing us. Okay. Okay. A Hall effect element used for measuring the magnetic field strength. Now, it's very interesting. One of the applications of the Hall effect is to measure the magnetic field. Okay. For example, in some applications, you need to measure the magnetic field because you want to, for example, in MRI machines, magnetic resonance imaging machine, you want to make sure that the magnetic field is constant everywhere or as constant as possible. So you might need to measure the magnetic field in different locations. For this, you can use a Hall effect element. So a Hall effect element used for measuring magnetic field strength gives an output voltage of 10.5 millivolt. What do they mean by output voltage? What is this output voltage? So the output voltage of a Hall effect, a Hall element, is the potential difference that is measured between the two sides of the Hall material, semiconductor or conductor. So the output voltage, the Hall voltage is 10.5, 10 to the negative 3 volt. Okay. The element is made of silicon and is 2.5 millimeter thick. Okay, so what is the meaning of that? The meaning, for example, if I have this element is thick here, or yeah, for example, in any situation, so the voltage is here, okay, and carries a current of 4 amps. 4 amps. The Hall coefficient, we are given RH, and we are given the distance, the thickness, the D is 2.5, 10 to the negative 3. And the question is, calculate the magnetic field. When we know that the Hall effect, the Hall electric field is equal to, the Hall electric field is equal to the current density times the coefficient, the Hall coefficient, times the magnetic field. So we want to calculate the magnetic field, right? Now, what do I need? I want to calculate the magnetic field. This I have, but I don't have this, and I don't have this. Okay. So how do I calculate this? So it's a cube. The silicon is a cube.
So to calculate the electric field, we use E equals V over D. So it will be 10.5 millivolts over 2.5 millimeters, but we have to convert to meters, I guess.
Yeah, exactly. So it is equal VH divided by the thickness, which is 10.5, 10 to the minus 3, divided by the distance, the thickness, which is 2.5, 10 to the negative 3. Okay, very good. Okay, we have now the electric field. What about the current density?
It's equal to the current times the area, right? So we have the area already, we just divide it.
Yeah.
I mean, we'll multiply by the current.
Yeah. So,
oh, sorry,
yeah. So the J is equal to the current divided by the area, and the current is 4 amps, and the area is, because it's a cube, is 2.5, 10 to the negative 3 and squared. Okay, and then we get everything, and then we can get the magnetic field. Any questions? Okay. So I will later I will give a review session before the exam, but remember the exam is in 2 weeks from now. Okay. So let's start another topic in the same chapter, and this topic is the electromagnetic waves propagation in solids. Electromagnetic waves, propagation of electromagnetic waves. And this is very important for electrical engineers, because most of the waves that you, I mean, most of the signals that you are dealing with are electromagnetic waves that are propagating through solids, either through dielectric, through conductors, through semiconductors. So you need to know how to misbehave. And interestingly, we will see that some electrical properties, why do we want to know this? This course is about electrical properties of materials, okay? In fact, it seems that, and we will demonstrate it, that the properties of materials, of some materials, change or are affected by the nature of electromagnetic waves that travel through them. Okay, electromagnetic waves that travel through this medium, through these materials. Okay, so this is why we want to the properties of materials change electronic property or some electronic properties of materials some electronic properties of materials change by the nature of electromagnetic by the nature of electromagnetic waves that cross or travel through those media, and you will see. I just want to go back to Shok is asking me a question. Maybe I went too fast. What was the no, Shok. In fact, the electric field is equal to the potential difference divided by the distance, by the thickness. Okay, and that's why the unit of the one of the units of the electric field is volt per meter. Okay. Okay, so I thought I made a mistake. Yeah, thank you anyway. Sorry for that. So how do we do this? Let's use Maxwell's equations to try to understand the following. I will consider a material. I will consider a material that is an electromagnetic wave that has, you know, electromagnetic wave. What does an electromagnetic wave has? Has a wavelength, frequency, rotational frequency, or the frequency. It has and then a material. So the wave has the frequency, angular frequency, and the wavelength, magnitude. This is for the electromagnetic waves. And then for the material is characterized by the permeability, the permittivity, the conductivity, resistivity, etc. So what I will try to do is to describe the propagation of a material, of a wave, electromagnetic waves, across a material, and see what happens using the Maxwell's equations, very simple equations, what happens to the material properties when for example, the frequency of the wave change, when the material has a high conductivity, low conductivity, or when the material is a pure dielectric. This is our work that we will do now. Let's summarize or remind you about some equations. We have already seen that the current density in a material is equal to the conductivity times the electric field. We know that the magnetic field is equal to the permeability times the the magnetic flux. The magnetic flux density is equal to the permeability times the magnetic field, and yeah. So the mu is the permeability, which is in Henry per meters. And you know the conductivity, the permittivity, and so on. Let's write two very useful Maxwell's equation that will help us. This is the Ampere Maxwell rule or law, or it tells us the following: 1 over mu nabla cross the magnetic field is equal to the current density plus epsilon and in fact this. So let me explain. A cross product. This one is the cross product. This one is the cross product. This is what you wanted to ask. Okay. this one, nabla. Okay, I will explain it. I will explain it. Yeah, I will explain it. Okay, I will explain it. So let me explain it here. Some of you have already seen followed physics 322. Can you please tell me if you have already followed physics 322? 322.
Do you mean ECEN370?
No, sorry. Yes, ECEN322. There is no physics 322. Some of you have already followed, some of you know. But anyway, let me do for everyone. So nabla is an operator. Okay, but anyway, okay. So nabla is an operator. This operator is actually it's the divergence of a vector. It gives you the following: Ex plus y ey plus z. Okay, so this is what is this? This is just, for example, if you apply this to a vector, cross a vector, you will just calculate, let's say this is the Ex, Ey, Ez, and you will use, this is X and Z, and then the dimension or the coordinate of the vector, the component of vector by, bz, and then you can do the calculation. This is the divergence of a vector, and this is nabla. It's an operator. It's a divergent operator. When it is applied to a vector, it's called the divergence of a vector. Is this what you wanted to ask? Okay. So yeah, so the Maxwell's, can anyone tell me what is the meaning of this Ampere's Maxwell law? So when we have the magnetic field that is changing as a function of time of space will induce an electric field that is changing in time. So this is the relationship between the electric field that is changing as a function of time and the magnetic field that is changing as a function of time, which means if there is an electric field that is changing as a function of time, it will induce a magnetic field, okay? So this is the Ampere's law. There is also Faraday's law. Faraday's law, it gives us the opposite. When a magnetic field changes as a function of time, it will induce an electric field that is changing in space. So Faraday's law gives us the following. Is equal to. So we will use these two equations, and these two equations, they have the properties of the material and the wave. Okay, they have the properties of the material of the wave. What are the properties of materials? There, J has sigma, mu, and epsilon. Okay, so those are the properties of the materials. The conductivity that is included in J, and the permeability that is affected by the magnetic field. This is permeability of the material, and the epsilon, right? What is the parameters of the waves? Parameter of the waves are included in the magnitude of E and B, in the expressions of E and B. E and B, those are the electric field and magnetic field produced by these electromagnetic waves. And there we will see that there will be a wave number, we will see it later, omega, and the frequency, and so on. So we have the parameters of a wave and the parameters of the materials. And now we will solve with some simple equations of assumptions. We will solve the equation to try to determine what happens to the material's properties when this material is crossed by a wave. I will stop here for 7-8 minutes. Let's come back at 5:20. Okay, I will pause the recording. Okay, and I will stop first sharing, and we will come back. Okay, no, I will zoom. Yeah, I will share the screen. I started the recording again. I resumed the recording. Now, the goal of this is not to do a lengthy calculation. Can you hear me?
Yes, Professor. Okay,
so the goal of this part is not to do a lengthy calculation. Actually, I just want to do this calculation in a simple way, and to show at the end the most important equation that we will derive and that we will use later. So to avoid any lengthy calculation, we want to do some simplification. So let's consider only one case. So some simplification. And there are several textbooks that gives the full calculation, but let's do just some simplification, because then the final result will be the same. Simplification is we will consider one case only, one dimension, sorry, one-dimensional case. One-dimensional case means that we will not look at what happened at the y-axis and x-axis, which means the propagation of the wave will be along the z-axis. And also, let's assume that this is the first simplification. The second simplification, let's assume that the electric field has only one component along the x-axis. Okay, now what do I want to do? I want to calculate this quantity and this quantity. Okay, so the first quantity will be nabla cross E. As I mentioned, nabla cross E is equal to the unit vector. I'm using EX, EY, EZ because in my node I use them, so that I don't want to change them. And then nabla is 0, 0, and then the derivative, the partial derivative with respect to Z, because this is what we did here, the assumption. And the E has only one component. Now you can easily see that we can calculate this cross product by so along the X it will give you 0, along the Z will give you 0. The only thing is along Y, and along Y it will give us so it will give us the derivative with X with respect to Z dy. This is because if you do this, you do this minus. Okay, sorry, for some reasons I got disconnected. Can you hear me? So I will share.
Yes.
Okay. So what I was mentioning is that this cross product is equal to this, and this means that, let me just give a number. This will be equation 1, this will be equation 2. So equation 2 becomes the derivative of X with respect to Z is equal to minus the derivative of By with respect to T. Why? Because By is, B is By Ey, and this one is also along Y, so I just get rid of Y because it's one dimension, and then I get this equation 3. Okay, are you following? Now I can also go and calculate this equation, nabla cross B, because I need it. I need nabla cross B. Again, nabla cross B is equal to Ex, Ey, Ez. And as I mentioned, I consider only the variation along the x-axis, the z-axis, sorry. And then B is only along the y-axis. And this will give me minus, you can easily calculate it with respect to Z and along the x-axis. So I replace this in the formula 1. So this gives me 1 over mu the By Z Ex is equal to J plus epsilon, the derivative of Ex with respect to T. This is equation 1. So 1 gives me this, and this is along Ex, because Ex is along the x-axis. Now we know that J is equal to sigma E. So this equation becomes 1 over mu minus By Ex, and this is equal to sigma Ex the vector plus Ex T Ex, which all of them are aligned along the x-axis, which I can get rid of them. So now I have two very important equations. The first one is this one, minus by, the partial derivative of by is equal to mu sigma ex plus mu epsilon, the derivative of x with respect to t. This is the new Ampere's Maxwell with the simplification that I did. And the second one, which is this one, the equation 3, Ex with respect to z is equal to minus by respect to t. And this is Faraday's law. Faraday's law after these simplifications. This one. Okay. Any question? Now I have two equations, and those equations gives me the following. As I mentioned, they give me the propagation of the magnetic field. They give me when the electric field changes as a function of time, it will induce a magnetic field along this direction that is changing as a function of z. And the Faraday's law, it's the opposite. When the magnetic field changes as a function of time, it will give me an induced electric field that is changing as a function of z. Now let's give what is the consequence of this. In order to finalize or to give the final solution, I want to consider a simple electromagnetic wave. And the simple electromagnetic wave is the following. A general form of the electromagnetic wave is Ex, because Ex is propagated along the z-axis. It is equal to a constant, and any wave form, the general wave, minus kz. This we have already seen in electromagnetic in ECEN370. We have seen also in physics 207 in electromagnetic waves, and we have seen also in physics 222 that's a general wave. It has this formula, and so k is the wave number, and omega is the frequency, angular frequency that we all know. And the same thing, the by can also be b0 and b0 exponential minus I omega t minus k. Now, what is the next step? The next step is replace these two ones into the two equations. I will call them equation 5 and equation 6. So what did we do here? We started by the Maxwell's equations, which gave us what is the relationship between the electric field, the magnetic field, and that are propagating through a media, to material. We give just some approximations, and we end up by equation 5 and 6 that relates the change in electric field, magnetic field, and the consequences of the induced magnetic and electric field in a media that has permeability mu, conductivity sigma, and the permittivity epsilon. Now I want to see, okay, what happens? Can I get something that is very interesting if I replace the magnetic field and electric field with a real wave? So we know that the derivative of let's say of Ex with respect to t or to z. So what will be the derivative? The derivative will be I K, and EX, right? The same thing, the derivative for By with respect to Z will be also the same thing, I, K, By. And the derivative with respect of EX with respect to time will be minus I omega EX, right? And the derivative By with respect to time will be minus I omega B. And then I replace, so I replace in these two equations, and I obtain the following. I obtain this equation. I obtain A I K E X is equal to I omega By. And minus I K By is equal to mu sigma Ex minus omega mu epsilon Ex. Those are the two equations. These two equations has the following unknowns. Has this Ex and this By. What I want to do, I can cancel those two equations. If I, well, yeah, which means I can substitute Ax and Ay. If I substitute, I can easily substitute, by the way. And if I substitute this, I will end up with this. You can do it. I will not do the calculation, but it's easy to just, well, one way to do it is Iakx Ex is equal I omega By, and then mu sigma minus I omega mu epsilon Ex is equal to minus Ik By. So you can do the ratio. You can do the ratio, and you can see the ratio will cancel. Ex will go, and By will simplify. And then we will obtain very, very important equations in electromagnetism, actually electromagnetic waves. This is K squared, which is the wave number, minus I omega mu sigma minus I omega mu epsilon equal to 0. This is called dispersion equation. This is called dispersion equation. Why this equation is very important? This equation is very important because it gives us one simple equation that relates the wave properties. You know, the wave properties are K and omega, and it relates them to the material properties that are, of course, mu, sigma, and epsilon. This is why it's very important. And you will see the consequence of this. Any question? So for me, the most important thing will be to understand this dispersion equation. The way we reached it, you can, I mean, you can look into the steps that we did, but this is a very, very important equation. And before going further, do you have any question? Okay, so now let's discuss this equation. This equation, dispersion equation. Let's discuss if the material is a dielectric. Okay. What is the meaning of the material is a dielectric? So here. So what is the meaning of material is a dielectric? Can you hear me? I'm I'm not speaking alone to myself. Hello, can you hear me?
Yes.
Okay, because it has been almost 10 minutes, nobody spoke, so I thought maybe I'm just talking to myself. Okay, so now, what is the meaning of a dielectric? What is the change to this equation, to this, if it is a dielectric, if the material is dielectric? What did we say? I said that this equation is very important because it relates the wave parameters, which are the wave number. The wave number will give you the wavelength, and omega gives you the frequency, to the material that is traveled by this wave, that this wave propagating to this material. So, okay, dielectric, a pure dielectric. Okay, a good shock, but a pure dielectric means a very, well, actually zero conductivity. Pure dielectric means conductivity is zero. If the conductivity is zero, this equation becomes k squared minus I omega. This is, so zero here, minus I omega mu epsilon is equal to zero. So this means that k squared, this is minus is a plus, and so it's minus omega mu epsilon is equal to zero. And k squared is equal to omega squared mu epsilon. Okay. Are you following? This discussion is very important, and I can tell you most of the time it's 20%, 25% of the exam. So k squared, and this you need to know as electrical engineer, this discussion. Okay, this we are talking about the case of a dielectric. The case of a dielectric, this means that the wave number is equal to omega square root of mu epsilon. So the wave number is equal to the angular frequency, the square root of mu epsilon. Now, what is k? K is 2 pi over lambda, right? Is 2 pi over lambda. And according to this, it is equal to 2 pi, the frequency, sigma mu epsilon. Are you following? Did you understand what I did? So the wave number is given by 2 pi divided by the wavelength, right? But according to these dispersion equations, it's also equal to 2 pi f square root mu epsilon. This is only for the dielectric, right? Now, 2 pi over lambda is equal to 2 pi f square root of mu epsilon. I get rid of this, I get rid of this. This means that 1 over lambda is equal to f mu epsilon, right? Let me continue. Okay. This means that lambda is equal to 1 over f mu epsilon, right? 1 over f is the period of the wave. So lambda is equal to 1 over mu epsilon times. So what is this? Lambda is equal something times t. What is this?
This is the period.
Sorry?
The period.
No, this one.
Oh,
Lambda.
I'm not sure.
lambda, a distance, is equal to something times time. Let me see. Velocity, exactly. This is the speed. This is the speed of the wave. The speed of the wave in this material. So K is equal to omega divided by the speed of the wave. Cm is the speed of the wave in the medium, in the material. Okay? Okay. So I will stop here, but this is a very interesting remark here. So this way you will see that if the material is a dielectric, sigma is equal to 0, the dispersion equation gives us a way to calculate the speed of the material, the speed of the wave in the material. And you will see that we will demonstrate that the wave is not attenuated. So the wave is not attenuated. So on Tuesday, we will demonstrate that if sigma is not equal to 0, which means in case of a conductor, the wave will be attenuated. And so I will stop here, but this is the importance of the dispersion equations. Any question? Any questions about it? So I'm not sure if next next Tuesday there is a match also. So we will be doing it online. So maybe I will do a quiz on Sunday. I will inform you by Tuesday. Okay. So have a good night and see you on Tuesday, inshallah. Okay. Thank you. Bye-bye.